from linear transparency and talking about spreading of the problems. I'm sure Pat will have a lot of things to say about it.
Thank you. Thank you, William. It's a great pleasure being here again, invited to a conference, which is a great event which I always love to participate. So my topic today will be turbulence spreading in anomalous diffusion on comms. By turbulence spreading, one means a process which turbulence initiated in some location can penetrate into surrounding stable areas. We know this term starting from works by Théorie dating back to 1994. And since then, the process was studied by many authors in a multitude of different settings and for different types of turbulence. So we know much work done the context of hydrodynamical turbulence, in particular in context of atmospheric turbulence, like spreading of thunderstorms. Then in fusion research, it's countless number of works dealing with various types of turbulence we observe in tokamaks, and especially in terms of edge-soul coupling, and the idea that edge turbulence can penetrate into soul via coherent structures like lobes or filaments. And so these ideas are about there since at least 25 years or so. Then in astrophysical context, there is a process like coronal mass ejections, the subject matter of talks from yesterday. When we get a coronal mass ejection by sun, Earth, sparkling, staging, and beautiful auroras. So everyone working in Nordic countries can appreciate the phenomenon and get interested in the phenomenon of turbulence spreading. But my motivation today will be a third public presentation of very recent work. It was Physical Review E, published 24th of June, actually very recent. So I still don't have much experience in presenting this work to the general public, but I will try. So the title of this work is same as title of my talk, and the motivation comes from quantum physics, from understanding of Anderson localization. I presented to you these topics actually several times before, 2 years ago in Marseille, and last year in Cambridge. And this is kind of curious, since I have motivation coming from quantum localization of chaos. No, we know after Roat's cave that every meaningful problem in physics is rooted in or comes from plasma physics. So today I'm going to reverse this paradigm and present you something that is not probably related with so much with plasma physics. But you know, when I mentioned this intention to Sasha Yeoman, my co-author from Théorie, he said that Sasha, we have same name, Sasha, no way. What you are talking about is quantum localization of dynamical chaos, and chaos comes from tokamaks. So just take the full route. Everything you are talking about is born of plasma physics. No way. Sergey was right. Don't reverse what he says. So, since we are at Theory Festival and we have also younger participants, I will allow myself to say a few words about Anderson problem, then I turn to new stuff. So, what is Anderson problem and why it inspired me that much? Actually, this is a very simple idea, simple as far we can perceive it now. It's about the fact that disorder can localize a wave process. That is, you inject a laser beam into the electric disordered medium. Then for some frequencies, which are normally frequencies smaller than gap frequency in a semiconductor. You can generate a standing wave. And it is standing, doesn't diffuse and doesn't propagate through the medium because it is reflected by inhomogeneities. So there are multiple scattering paths to the wave process, and it remains localized. When you really inject something, then there is an interesting process, which is transient process, when you first generate and excite all meaningful unstable modes disordered medium. This is actually a very fast process, and it was a subject matter of intense investigation in this field. So after this initial process is accomplished, what you get is actually a standing wave with exponentially decaying profile, and that can live in a disordered medium for quite some time, much longer than the characteristic inverse frequency of the wave. So this is linear. This phenomenon was cited by the Nobel Prize in Physics in 1977. You know, Anderson published his work in 1958 in Physical Review. And history says that his work was not even noticed for 10 years or something. Only 10 years after he started to get some first meaningful citations. And then it led to really expansion of interest in this phenomenon. Now we know that Anderson problem was at the origin of many interesting other developments, especially in solid state physics, like the understanding of the mode transition, or now a hot topic is many body localization problem. My interest in Anderson localization also began with my collaborations with Sasha Yeoman from the Technion, dating back to 70. I got to the very end of my talk, dating back to 2008. And he challenged me by saying that one can destroy the Anderson problem, the Anderson localization, by adding nonlinear term. That's he is linear, but add nonlinearity, and nonlinearity destroys the localized state. Why destroys localized state? Because nonlinearity essentially means an overlap between components of the wave field. And this overlap produces pressure that squeezes the wave function through the disordered medium, and the field can propagate to infinitely long scales. The phenomenon is described by Schrödinger equation. So dating back to Anderson, there is a special form for Hamiltonian, which is Hamiltonian tight binding approximation. Then you add nonlinear term and basically demonstrate that for some values of nonlinearity parameter, the localized state can be destroyed, for others it can survive. Now, why I think that this is relevant to plasma physics and especially to tokamaks? Because this linear Hamiltonian here, better to say, because the phenomenon of Anderson localization is not related to the specific form of Hamiltonian. It is not the property of the Anderson Hamiltonian. It is the property that your linear field must be localized by some process. And in tokamak physics, such process can be associated with toroidal geometry. So you can make your Anderson problem by saying that you inject a pumped wave into plasma, initially stable, and then you probably will have something like transient process in Anderson problem. But now with a different implications, so what you have decay instability. Decay instability means that the pumped wave undergoes a decay process. It goes into decay into 2 or 3 or maybe more waves. And if the injected power is sufficiently large, you can generate a cascade of secondary decay processes and so on. and this will go, let's say, as 3 or 4 wave interaction or high wave interaction. And in the end, you will get something like a small part of turbulence. Why of turbulence? Because when you start to get a certain number of waves that will indicate stability, sooner or later, you will come to four-wave scattering processes. They don't come into play just from the outset. The outset, you have one wave which must go into decay stability. But when you couple sufficiently large number of waves, they go into scatterings. And then there is a classic paper by Berman and Kolovsky, and also a second one by Berman, Kolovsky, and Théorie, could say that when you have sufficient number of waves which participate in scattering processes, this gives rise to stochastic instability, and the whole thing becomes chaotic, and you get not only a wave packet, but you have stochastic wave packet which can spread despite that it's linearly localized. And you go into a process which resembles Anderson localization and the destruction thereof. Then you can do your stuff. That is, you write nonlinear Schrödinger equation, nonlinear term. You know, if you have a linear wave, which is localized by potential field, then you have discrete spectrum, and you have full phases of eigenstates. So you can expand your wave function over the eigenstates, substitute, do some diagonality, multiply, sum, and obtain dynamical equations. And this is essentially a dynamical equation with 3 couplings on the right-hand side. Then you say that these 3 couplings, when you have many waves, is equivalent to a white noise process. You get a stochastic differential equation driven by white noise, and from that you derive actually an equation for field spreading. Alternatively, if one doesn't wish to use the nonlinear Schrödinger equation, which, by the way, is not that obvious, since introducing nonlinear Schrödinger equation is also a step which involves some specific assumptions. One still can do different by writing the interaction Hamiltonian for four-wave interaction process. And the subtlety there is that you write this interaction Hamiltonian just keeping into account that you have all forms of four-wave interaction processes, that is decays, merges, and scatterings. And this is justified by the fact that you consider your wave at a stage when you have bypassed the initial excitation stage, and you have actually something that expands slowly, and you have merges that roughly compensate for the decays, and you have scatterings which produce stochasticity, and so forth. And then you apply canonical equations, and you get your dynamical equations exactly in this form. Of course, 2 things are mathematically related, because linear Schrödinger equation with quadratic nonlinearity basically implies that you have four-wave interactions in the nonlinear term.
Can you remind me where the Anderson type disorder is hiding? It's in H sub L?
Yes. Yes.
And that is what a solid state analysis would call quench disorder.
Yeah.
It's frozen. It does not.
Yes, exactly. Right. Exactly. If you allow for disorder to be time dependent, then it's another way to destroy. Okay. Yes, you're right. HL is tight binding Hamiltonian. All right. Now what you essentially have? You have your components of nonlinear field time dependent, where the evolution of the components is given by these 3 couplings on the right-hand side. This immediately gives you the rate for field spreading. Rate of spreading is intensity of nonlinear coupling. Take the coupling term squared, and this is the rate. Which is the rate now? In quantum physics, you write the rate according to Fermi's golden rule, and same applies here. It applies here because your waves must be resonant. Each time when you produce some waves, they should satisfy the obvious conditions for momentum and energy conservation. There are resonant conditions, and due to this resonant condition, you write golden rule. That is what you have here. You have R, which is infinity of number of states, and you have nonlinearity on the right side, which is inverse of delta n cube. There is no way you would not obtain this behavior, because this is topological. This is topological because the structure of your nonlinear term is exactly the skeleton that you have always one coming and two outgoing waves, or whatever you call them, two incoming or one outgoing wave. There are always three, and you put your nonlinear Schrödinger equation on Théorie and demonstrate that there is no escape, that you get the nonlinear term exactly as it was written. And then we have my golden rule there, and on the right delta cube. So delta n cube, you consider that your probability is conserved across the wave packets, so it is spread over delta n states, then integral of delta of psi over delta n is 1, and psi squared there. So it is. And you integrate this equation and get the rate of spreading. This is asymptotic. And there is a multitude of ways you can obtain this scaling. You can use Hubbard model in quantum physics. You can check it in numerical simulation, and you get always scaling square root of time. And now we argue that this would be the spreading rate for the nonlinear field, linearly localized with quadratic nonlinearity. It is subdiffusive, and keyword here, subdiffusion, not diffusion, subdiffusion. And at this point, we would like to understand better what does it mean, because subdiffusive process can be something very different from ordinary diffusion. And that is essentially the heart of my talk today, to understand the origin and the way we can handle the subdiffusive process. To understand it better, why it is not diffusive and slower than diffusive. It's a...
Can I ask? Just because I don't understand. Look, the subdiffusion, are you formally deriving it, starting from the nonlinear Schrödinger equation?
Yes.
You are formally deriving?
Yes. Yes, because it results from the fact that you have nonlinearity on the interaction term. And you combine your Fermi-Golden rule with nonlinearity. And this produces to you subdiffusion.
In the sense that you have a derivative which is fractional.
No. I might have it and I will. But for the moment being, I have scaling. I don't know anything about kinetics, and I don't write equations yet. I will write them shortly, but I don't write them yet. So what I obtain that mean squared delta n behaves not proportionally with time, but proportionally with the square root of time. And this is scaling. And this is subdiffusive scaling. Now I want to understand why it is subdiffusive and not diffusive. And one reason for this, basically the reason for this, is that you have your very special nonlinearity due to a nonlinear Schrödinger equation. How you demonstrate? You rewrite your rate of spreading infinity delta cube. So we differentiate both sides with the equation by time. So dt, there's derivative, differentiate on the right hand side minus d delta n4. dt delta n. And this guy here, you take it here, substitute, obtain 7 power, and then write the 7 power minus of the potential function. And this potential function then minus vector delta n power 6. And from this, you can see that this equation is a dynamical equation for a point particle moving the potential field, which is essentially the Lennard-Jones field. This is the directive part of the Lennard-Jones potential, which we know from molecular physics, and we know that this part holds together molecules. This is the directive part, which direct molecule together. And from this behavior, which we now obtain in delta space, Sasha Yeoman suggested that we have something similar to molecules in Fock space. It's around localization space. This behavior means that there is a directive interaction between unstable modes. These unstable modes form clusters in Fock space. They are held within these clusters. They are held within because they interact positively through Lennard-Jones potential. Because they are attracted, in the presence of this attractive interaction, it slows down transport, it keeps unstable modes together, and your spreading is slowed down. Therefore, you have a deviation from the diffusion process. Now, I wish to obtain an equation for that. How do I do it? Because I have an effective potential, I can say that the probability for a given mode to leave a cluster where it leaves the Boltzmann factor, which is the Lennard-Jones potential divided by temperature. Now, where does temperature come from? It comes from the fact that when you limit yourself to four-wave interaction zone, you forget about high-order terms. In quantum electrodynamics, you will get everything that goes above the terms where you limit your model. It goes like a perturbation. So everything starting from more than four-wave interaction is a perturbation that generates the temperature. Write this. I write Boltzmann form because the density of modes is low. I don't want any quantum units here. So the probability to quit the cluster after the steps, so the step is exponential factor, 1 minus the densities. From Lennard-Jones potential. Then the probability to remain in the cluster will be 1 minus this. Now I eliminate delta n, and I say that there is a probability to remain after delta t time steps. Delta t to the power minus 3/2. And this is curious, because now I have a process in which a mode, which is trapped within a cluster, it has a probability to exit from the cluster, and the distribution of exit times is powered off. And this leads us to continuous time random walks, where distribution of waiting times produces your memory and produces your fractional equation. Yeah.
Coming from inference, typically, if I want the probability distribution of first passage time, then typically I have to go to a Fokker-Planck presentation and then solve my Fokker-Planck equation, which is generally very difficult with anything other than 1D. But you seem to be able to get the probability distribution extremely easily. Is there a trick, or is it?
Well, I'm going to make a trick. Now I have two things solid. One is the fact that spreading rate depends non-linearly on the number of states covered. So DDT of delta n is inverse of delta n cubed. It's one thing. From this, you obtain subdiffusive scaling. From this, you show that this is equivalent to Lennard-Jones potential. Lennard-Jones potential gives you interactive interactions. From interactive interactions, you show that there is clustering and there is a power law distribution of exit times. As soon as you have power law distribution of exit times, you can obtain your mean square displacement as you want by using a proper jump function. And this I still don't know. And for this, I need comps. And this is why comps were on the title of my talk. Now I tell you about comps. So what is comp? Comp is a geometric representation of continuous time random walk. Mathematically, it is defined as a geometric representation of the Dirac delta pulse. So this is pulse function. have my x, it's called backbone, and I put what is called teeth or side branches, vertical steps along the backbone. And I select arbitrary point here as my origin. So it's a bit complex geometry, a kind of graph. And I want now to set a dynamical process in this geometry. So what I do, put a random walker here, and I say that just keep him way along the T, up and down, unimportant then. And I say that I random walk a particle participate in a diffusion process along the backbone, along the side branch. So what happens next? If this is diffusion, then I know Green's function. And the Green's function will be like this, yt. It will be 1 over square root. If I'm a purist, I write 2 pi t, but I don't need 2 pi. Exponential minus delta y squared for ky t, where ky is the diffusion coefficient. That is, when delta y is 0, that means that I have a non-zero probability to return to the starting position after t time steps. And this going to decay is 1 over square root of t. And the density of this probability will be the time derivative of this power of function will be 1 over time to power 3/2. Which means that if I wait long enough, I will almost come back here. When I come back to starting position, what happens? I will say that with probability 1/2 nothing happens, and I continue my diffusion process on teeth. And with probability 1/2 I jump, and I jump either in the direction of x or in the opposite direction, unimportant. So before 1 instant, and so forth. I write here, I make my diffusion process until I press the backbone. Then again, I jump or not. And I look over it for infinitely long times. Then what I do, then I obtain that there is a random walk process on backbone with a distribution of waiting times. And this is exactly the continuous time random walk, which, as we know from outstanding people, leads to what one calls fractional diffusion equation, an equation with fractional derivative over time. This is fine, of course, but this is tricky. This is tricky because I can avoid writing my fractional diffusion equation, and I can simply write a Fokker-Planck equation in comb geometry. That was exactly the comment we received a few minutes ago. And I can write my Fokker-Planck equation in comb geometry in a very simple way. So there is a probability density. I write partial t derivative. So I have diffusion in teeth. Then I have second derivative over y, f, plus I have random walk process along x. So I have second derivative over x there. And here I have kx, and here I have ky. And the thing now that this diffusion coefficient over x depends on y. It depends on y because I take my steps along x only when I cross the backbone. So I can go along x direction only when I'm at 0 position here in y. Therefore, here I have a constant multiplied by delta function of y. And so now I get my two-dimensional Fokker-Planck model, which involves coupling between x and y coordinates through delta function here. And this model doesn't contain fractional derivatives, but you can solve it. You can solve it using Laplace transform. And this is exactly what is reported in my paper in Physical Review in appendix. The derivation in 2 pages leads you to subdiffusive scaling over time. And you get from this that Planck equation without any fractional derivatives can be reduced to equivalent effective 1D form, writing the equation in 1D, but in terms of fractional derivative. So you may choose now having a 2D Fokker-Planck model without fractional derivatives, but with delta coupling and diffusion coefficient, or demonstrating that this is equivalent to a 1D equation with fractional derivative in time. This is, by the way, what Fulvio Militello tried to convey during the first week. He reported that when he goes into simulations, it is much more efficient for him to solve fractional diffusion equations than to solve 2D or whatever he has transport models, because full transport model is time consuming, and he found out that if he reduces stuff to fractional derivatives, he can integrate very easily. And this is the motivation for this. Actually, it gives some insight what fractional equations do mean. It was an important topic and sparkling some debate in community, what we do mean by fractional derivatives, by fractional derivative equations. So we mean reductions of more general 2D models with coupling, delta coupling between degrees of freedom.
I don't understand why your alpha and beta in the fractional kinetic equation would come from in this picture. Like how do you get your alpha and beta in
1 minute. Now I get my alpha and beta. If here is a diffusion, the probability to return is 1 over square root of time. Okay? The density of the probability is 1 over time to power 3 halves. And this is exactly what we get from Lennard-Jones potential. So the conclusion is that if you take a random walker, which takes 1 unit step along the backbone with a distribution of waiting times, as it is suggested by the Lennard-Jones potential, but without a distribution of step sizes with a characteristic jump length, then everything converges. So you get your transport equation in the form written here. This guy comes from the fact that you take 1 unit step along the backbone without distribution of jump length. And here your alpha is 1/2. So I think this is the equation which describes your spreading by 4-wave interactions. And you will see from this result that 4-wave interactions don't produce anything like non-local behavior. So your thing is normal program, that is something made with time derivative, you have memory, but you have jumps which are distributed according to a Gaussian law. So you don't have jump length distribution, you have everything like in standard central limit theorem. There is no way you can produce non-local behavior in 4-wave interaction. The proof comes from the model. Now, of course, you're unsatisfied with this and you want to see what happens if, how to obtain non-local behavior, or what happens if I go beyond my 4-wave interaction scheme. I have to generalize my 4-wave interactions and look further. And one possibility would be then to say that now we want to look into 3-wave interaction processes. So how much time I have, by the way? Then in the rest 5 minutes, I will explain you the most interesting things. The most interesting thing here is that I wish now to relax my 4-wave interaction, the pattern, and consider 3-wave interactions. In Anderson problem, this leads to enormous difficulty, because then I should write my nonlinear Schrödinger equation with a power which is not quadratic. You write it with subquadratic power with S, which can be 0 and 1. This is difficult. It is difficult because you have modulus function, it's not analytical. To handle it, we had to develop some mathematical formulas. I delivered it in Cambridge last time. Main thesis here, there's such type of equations, subtractive reductions of more general equations with non-local nonlinearity. To deal with non-local nonlinearity, we had to develop multinomial expansion, demonstrate how all this stuff can be mapped not on simple Kelly trees, but on Kelly forests. We have iteration procedures here which correspond to the different levels of mapping onto Kelly forest. In the end, we get what we get in terms of transport equations are Levy noises. And Levy noises generate something like a non-local derivative in space. So the message here that to get non-local behavior, you need 3-wave interaction. But it's appears to be too difficult. Finally, I want to advocate you comps. On comps, you can solve the problem almost like immediately. You write your Hamiltonian for 3-wave interaction process. Apply canonical equations. From canonical equations, you get your reading rate. Now it's in terms of delta n squared, not delta n cubed. And combine with Fermat golden rule. From this, you get subdiffusive scaling, transport scaling, and you repeat your part with then of your potential, which now like inversal of power of delta n of 6 power. And you put it on a comp. So you have now dispersion and you have waiting time distribution. Now you put it on a comp. And from this, you will find out that there is no solution. There is no solution until you perform 1 unit jump in random direction along the backbone. So to solve it, you need to generalize your comp. And you need to argue that now you want to have your teeth everywhere densely along the backbone, and you also must allow for distribution of jump lengths along the backbone. It's one story. Another story that you have to generalize a bit the diffusion process in teeth and say that you would like to model them as fractional Brownian motion. Then you can solve the problem and see that everything matches perfectly. There is a linear distribution of step sizes along the backbone. And from this, you obtain your fractional equation with right for 1/3 because it comes from waiting time distribution. And the operator here with Levy continuum 1, which means that you have an unlocality of Lorentzian type. So this is the exact result. You have this exact equation for 3-wave interaction. So this equation is non-local. You get non-locality only after you have involved 3-wave interaction process to the model. So to this end, we have essentially discussed 2 things. We have discussed 4-wave interactions which produce Markovian dynamics, but without special non-locality, and 3-wave thing which produces your non-local dynamics with memory. So 3-wave interactions are simpler, but they are more complicated. And these are 2 main partial cases of the model. So I will about to conclude now, but I will conclude with challenging you. Just thinking to what we know from plasma physics. We remember, of course, such basic things as Maxwell-Vlasov model. And we remember what Vlasov did when he obtained his system of equations. He made some integration, dispersion relation, and 2 co-integrals in principal value sense. Then Landau came and he said, no, there is a pool. When you go with your integrals over the pool, you have to do it carefully. And there is something happening at 0. And from this, we know this Landau-Daly is about. So there is something similar in this business here, and this is the zero frequency resonance. So far, I implicitly assumed that there are no zero frequency resonances, but if they occur, they can change very dramatically the whole thing. And the zero frequency resonance is something which we meet in tokamak plasma. For instance, we think about it when we look at zonal flows or staircases. So, again, already familiar with this plot obtained by our colleagues from AVM, by Guglielmo, which demonstrates the phenomenon of staircase with some turbulent spreading. So here spreading, I guess, between the staircase jet, jets of avalanches, so basically that there is something local going on. Initially, I thought that this the staircase problem can be solved using three-wave interaction paradigm, because three-wave interaction local non-Lorentzian canal. But a closer look says that it's not as simple as it looks like, and we need to be a little bit careful about how our waves propagate. Somehow we know from basics of zonal flow physics that zonal flows occur through zero frequency resonance between running drift waves and standing a fluid wave. So if you write interaction Hamiltonian now for interaction process between a running wave and the zero frequency wave, you write it essentially as a three-wave process. So you will have a process like sigma k star, sigma 0, sigma k minus 0 for the falling drift wave, zero frequency wave, and the running away drift wave. But because it is zero frequency, it's you may imagine it as a complex wave, like a hadron particle that is composed of two coupled wave processes inside with oppositely directed momentum. So we write it's like sigma minus g sigma g, and this goes to your interaction Hamiltonian. And when you write it this way, you will get it like a four-wave interaction Hamiltonian. So you can have to choose whether you like it as a three-wave process or a four-wave process. And the question is what you have to choose. And the answer which we propose is that you have to choose both. There is a duality in this process. Your system with zero frequency resonance can behave both as a three-wave and as a four-wave system. But when? It behaves as a three-wave system when it comes to spreading rate, because your spreading rate is limited to the occurrence of zero frequency states. And this is essential. It limits your spreading rate to occurrence of zero frequency states. But when it comes to lifetime of such states, you should choose four-wave process, because four-wave process decays faster, and it will have an upper hand in determining the lifetime of such states. So you can consider a case of mixed statistics, when you have three-wave process which determines to your asymptotic spreading, and the four-wave process which determines your lifetime and the distribution of exit time. And then you put it on a comp, and you consider a comp space where the distribution of return times comes from four-wave processes, the ground function comes from three-wave process, and you solve it. And the solution is immediate. You obtain a bifractional equation with alpha 1/2, because it comes from four-wave interactions, and with the Levy index mu, which is exactly in the middle between your four and three-wave cases. In four-wave case, you have it 2. In three-wave case, you have it 1. In this case, zero frequency resonance, you have it 3 halves. And then you refer to something like to numerical evidence. Numerical evidence gives you a way to calculate size distribution of avalanches and connect the size distribution to the Levy index. And this work was done by Guglielmo. We had a paper together in 2021, which suggested a parameter in this distribution is given by what you obtain from home, that its parameter is inverse of Levy index. Levy index is 3/2, so theory predicts that this half parameter is 2/3. And at this point, I cannot care less about comparison to numerical simulation. So instead of summary, just put here the various exponents which could be calculated separately for 3-wave processes, for 4-wave processes, and for staircase physics and zero frequency resonance. The conclusion here, so 4-wave interactions don't produce non-local behavior, but they produce something with memory. 3-wave processes produce both memory and non-locality. So if you want non-local behavior in fusion plasma, you need to go to 3-wave interactions. In staircase, zero frequency resonance is special and produces very peculiar behavior, which is both non-local and heavy memory. And the comp model predicts all exponents that you want to have here. So thank you for your attention.